Hi everyone, welcome to Friends of Optimization. This is a joint seminar series run jointly by Professor Ernest Rio at UCLA and OpenAI and me. So I'm Shubha. I am an assistant professor at Rice CMR. So today we are very happy to have Daniel Cederberg, who is a PhD student at Stanford University. He is going to talk about his very exciting work with his co-authors on disciplined nonlinear programming. Daniel is a PhD candidate at Stanford University. Prior to joining Stanford, he received BSc in physics and an MSc in applied mathematics, both from Linköping University. I hope I said the name right.
It's fine.
Uh, okay. So his research focuses on developing optimization algorithms and accompanying software. His works includes PSLP and LP presolver used in solvers such as CUOpt, as well as nonlinear programming extension of CBXPy. In summer 2025, Daniel served as the instructor for Stanford's renowned convex optimization course EE364A. So without further ado, let us welcome Daniel.
Yes, thank you very much for that kind introduction, and thank you for having me here. It's funny because there are always two people describing you in a very nice way. The first person is your mother, and the second person is the person introducing you to give a talk. So, yeah, thank you for that very friendly introduction. So today I'm going to present some joint work with a few collaborators related to Stanford, William Sang, Parth Noble, and my advisor, Stephen Boyd. And these have been, excellent collaborators. And in particular, I want to highlight William here, who has been an amazing person to work with. So the title of my talk today is Disciplined Nonlinear Programming. And this talk is essentially about a new modeling language or modeling framework for nonlinear programming. And if you have used nonlinear programming before, you should be a bit skeptical about this word disciplined here. Because typically in nonlinear programming, you are allowed to formulate problems in any way you like. You then pass them off to a solver, and you hope that the solver will be able to solve your problem. But we will see that in our modeling language, there is some kind of discipline. There are some kind of rules that you must follow. And one of the purposes of today's talk is to convince you that it makes sense to enforce these rules. But before we talk about that, I want to say a few words about convex optimization. So here we have a generic convex optimization problem where we minimize a convex function. We have some inequality constraints, which are described by convex fi, and we also have some affine equality constraints. And I think it's sometimes useful to take a step back and ask, why do we actually care about convexity? Well, there are two answers. First, we have the very classic and academic answer, namely that convexity is great because for a convex problem, any local solution is also a global solution. We all know that. That's a classic academic answer. But there is also a more modern and pragmatic answer, namely that convex optimization is great because it is very actionable thanks to reliable software. So a couple of months ago, I met an optimization professor in Sweden, where I am from, and he is of the older generation, and I shared my opinion here that this is what makes convex optimization great. And I could tell that he was mad. He was actually furious because he said something like, how can you dedicate the beauty of convex optimization to something as trivial as software and not the elegant theory behind it? So at that point, I knew two things. First, I knew that I will never be able to, get a postdoc position at that university until he retires. And two, I knew that I would not be able to convince him of this second reason. So instead of arguing with him, I decided to ask him a couple of questions. So first I asked, when you were a PhD student 40 or 45 years ago, did you care about convex optimization back then? And he responded, oh, no, not at all. You see, back then, it was more about linear versus nonlinear programming. Because back then, we had some kind of software for solving linear programs. So it was actually doable with a lot of effort. But as soon as you wanted to solve more general problems like QPs, it was practically impossible because the software was not, available. So that was his answer. And then I asked him, do you care about convex optimization today? And he said, oh yes, of course, because today we actually have software that we can use to solve them. And at that point, he knew that he was caught in my trap because he had basically argued himself that, this is the reason why convex optimization is great today. So why do we actually have reliable software for convex optimization? Well, one of the reasons is this notion of disciplined convex programming. So if you just take an arbitrary optimization problem and you formulate it in an arbitrary way and give it to a computer, it is very difficult to verify that the problem is convex. So disciplined convex programming is a very simple grammar or mathematical framework for constructing convex optimization problems. And in this simple framework, there are some simple rules which tell you how you're allowed to combine and compose functions. So for example, if you compose two convex functions, under what additional assumption is the composition also convex? So this framework, disciplined convex programming, it specifies how we are allowed to compose different functions. And if you follow these rules that the framework enforces, you know that the problem you end up with is convex by construction. So this is a systematic way of constructing convex optimization problems. And I should point out that we are in academia, so we know that there are convex problems which are NP complete and which we can't solve efficiently. But if a problem follows these DCP rules, it is one of these normal convex problems, which we can actually solve globally and efficiently, both in theory and in practice. So, to some extent, if your problem is DCP, if your problem follows these rules, and as long as it is of reasonable size, you can actually solve it in practice as well. So disciplined convex programming is a mathematical framework. You can implement it in several different languages. So some examples of implementations include YALMIP, which was possibly the first DCP language. And we also have CVX, which was one of the early ones. Both are in MATLAB. But the most popular today is probably CVX Pi in Python. But what is quite interesting is that I learned optimization using AMPL actually. And AMPL, this classic commercial piece of software, does not implement a DCP. So they do something else to verify if a problem is convex, probably something more complicated. I don't know what they are doing, honestly. So we have these different languages implementing disciplined convex programming. What else do they help us with? Well, it turns out that these languages have two different main tasks. The first main task is an analysis step in which they verify that the high-level problem description from the user actually follows these DCP rules. So in the analysis step, they verify that the problem you specify is convex. And after the analysis step, there is also a synthesis step. And in the synthesis step, the modeling language takes your high-level problem description and transforms it onto a form that an underlying solver can understand. And exactly what this conic form that modern solvers for convex optimization are based on does not really matter. But something that I do want to highlight is that once the modeling language has formed this conic form, it takes the problem data, so the matrix A, the vectors B and C, and this convex cone K. The modeling language takes those quantities, pass them to the solver, and at that point, the solver knows everything it needs to know to actually solve the problem. So in other words, there's very little communication between the modeling language and the solver beyond this problem data defining the actual problem. And why do I mention this super weird detail? Like, who cares? Well, the reason I mention this is because we will see that in nonlinear programming, the modeling language actually plays a much bigger role. There is much more communication between the solver and the modeling language in nonlinear programming. And that's why I mentioned this. So finally, I just want to show you an example of how you use disciplined convex programming in practice. So in this problem, we have a matrix variable x, and this matrix variable represents an inverse covariance matrix of a Gaussian vector. So basically, you want to estimate an inverse covariance matrix. And we want this to be sparse for certain reasons, so we have added a sparsity regularizer here. So this problem is called a sparse inverse covariance estimation, and it has applications in graphical modeling. One application is called functional connectivity analysis, in which you can, construct these cool pictures of brains. I'm not going to try to explain what this picture means because, I'm not a doctor, like a real doctor of medicine, and I'm not a doctor of mathematics too, I guess. But I do know that you can construct this figure of the brain by solving this sparse inverse covariance selection problem. I do know that. So suppose we have agreed that we actually want to solve this problem. And suppose we want to try CivXPy to see if it works for the size of the problem. So then here on the left side, we have what the user sees. So we have a log determinant term in the objective function. Well, we just type it in. So it is extremely simple to specify the problem in CivXPy. So here on the right side, we have what the solver sees. So what CivXPy will do for us in the convex optimization case is to take this high-level problem description on the left side and canonicalize it or transform it onto this standard form on the right side. And this canonicalization, this transformation is sometimes, very easy to do by hand, but often it is surprisingly difficult. Because, for example, here on the left side, we have a log determinant term. That's a very nonlinear and nasty function. But here on the right side, everything is linear except for the cones. So, I think it's fair to say that for this sparse inverse covariance selection problem, it's actually impossible to derive this standard form by hand. I did it once. It took me 3 days. I was, young and naive, and I should never have done it. So we should be very thankful that we have these modeling languages that canonicalize problems for us. So that wraps up what I wanted to say about convex optimization. But what can you do when your problem is not convex? At Stanford, we teach a class in convex optimization where we show the students a bunch of applications in which convex optimization problems naturally arise. And we also show them some applications in which the problem is non-convex, but you can find an equivalent convex formulation by applying some tricks. And one of these tricks is to do a change of variables. So for example, if you are in statistics, you might have heard of the fact that if you do maximum likelihood estimation of the parameters of an exponential family, that corresponds to a non-convex problem. But if you make a change of variables to the so-called natural parameters of the exponential family, then you actually get an equivalent convex formulation. So that's one example where you can convexify a non-convex problem by using a change of variables. So when you encounter a non-convex problem, you first want to try to convexify it. That's the ideal case. But unfortunately, it is rather maybe the exception than the rule that you can actually convexify it. So the next step you can do is to stare at your problem and see if there is some convex structure. And then maybe you can implement some simple heuristics like the convex concave procedure that takes advantage of that convex structure. So we have these heuristics of different taste tests that, they are pretty similar to some extent. But then we have this third approach, which we will focus on for the rest of this talk. if your problem is not convex, why not just try to apply a general purpose nonlinear programming solver? So that concludes my section on convex optimization. Now I want to say a few words on nonlinear programming. So now we switch focus to nonlinear programming. So here we have a generic nonlinear program where we minimize some function subject to some constraints and variable bounds. And here we make no assumptions on the curvature of the functions. So we have our problem is likely non-convex. But we do assume that the objective function and the constraint function, we assume that they are differentiable. That's the typical assumption in nonlinear programming. And I should point out that in this talk, we care about local solutions. Like we focus on classical nonlinear programming. I'm not going to talk about global optimization methods. That's a completely different topic. So this is the setting we care about. Differentiable problems involving differentiable, but not necessarily convex or concave functions. So,
Daniel, so I have one question.
yeah.
So are you assuming that the problem structure will, like the user will know L and U, or this can be?
Yeah, so if the user does not know that, they can just
Yeah.
specify it as infinite bounds.
Okay.
But we, like in the modeling language, we
Yeah.
derive bounds for you. So if the objective is like log of x,
Mm-hmm.
we automatically deduce that, okay, x must be non-negative.
Mm-hmm. Mm-hmm.
So we
So
help you with that.
that's like more like a domain, but
Yeah, precisely. We deduce domains of all the functions involved.
mm-hmm.
So
Mm-hmm.
if you satisfy these bound
Yeah.
constraints strictly,
Uh,
then you know that you are in the domain of F and C
okay.
in our implementation, but that's not the case for other modeling languages.
Mm-hmm.
I'm going to
Mm-hmm.
say a few words on that later.
Okay. Okay. Sounds good.
Thank
Also,
you.
everyone else, like if you have any question, please interrupt him anytime.
Yeah, thank you.
Yeah.
Yes. So yeah, actually, like a couple of weeks ago, I went to a party, like a real party with drinks and stuff, and there were like 50 people there, and of course I ended up talking with the only two people at the party who do some kind of optimization, and I realized that even among distinguished optimization researchers, there are some misconceptions about nonlinear programming floating around. So I want to show you some simple examples that hopefully will clarify some of these misconceptions.
Sorry, can I ask a quick question about the
Yeah,
previous formulation?
yeah.
Is f allowed to be extended real value?
Uh, it should not really, because in our modeling language, we assume that on this, uh, if you satisfy the bounds, then f is differentiable. So that would not support extended value functions.
So then this isn't all nonlinear programs. It's just the way you're framing nonlinear programming.
Um, yeah, I guess that's correct. Yeah.
Because it doesn't permit all horrible non-convex constraint sets.
No, but for example, if you have log is not finite everywhere, but we want to include the domains of functions in the bounds, so that if you satisfy these bounds, then you know that these functions are finite valued. We make that assumption to some extent, yes.
Yeah. My only point is that because you're only looking at bound inequality constraints, you can't capture all nonlinear constraint sets, like all non-convex constraint sets.
I'm not sure about that because we can always introduce new variables.
Oh, okay, maybe that's true.
Yeah, but let's think about that later. That's an excellent point.
Okay, interesting.
I always make sure to invite one very smart friend to every talk I give so they can question me. I recognize that voice, so yeah, thank you. But I was saying that I want to show you a few examples of misconceptions, to clarify these misconceptions. So the first misconception, well, it's not really a misconception. This is a warm-up because we all know that this statement here is not true. So the statement is that nonlinear programming solvers always compute global minimizers. This is not true, and to show this, we have this function here. We have the global minimizer here around -1, but if we start the algorithm here at x0, what will happen? Well, we will actually converge to this local minimizer. So this is exactly what happens for IP-opt. IP-opt is probably the best solver, the best open source nonlinear programming solver out there. And IP-opt converges to this local minimizer in 7 iterations. So that was a warm-up. But if solvers don't compute global minimizers, what do they actually compute? Well, maybe they always converge to local minimizers that are close to the initial point. Is that true? Well, this is actually our second misconception. So the statement is that a solver always converges to the local minimizer closest to the initial point. This is actually false. Because suppose we start here at x0. Where will we converge? Obviously, we will converge to this local minimizer because we are so close to it. In particular, we should converge in one iteration just because we are so close to it. So we should be in the region of quadratic convergence of Newton's method. But I have actually constructed, that's what you think, but that's not what's going to happen. Because I have constructed this function here such that it is twice continuously differentiable. So it is a nice function. This is the type of function that nonlinear programming solvers are designed for, twice continuously differentiable functions. So I'm not messing with that fundamental differentiability assumption. But I have constructed this function so it becomes linear here in the right tail. And since this function is linear, it has no curvature here. So the Newton step will actually be very, very long and take us into this region of the space. That's the intuition. And that's actually exactly what happens. So even though we start over here, you think you will converge to the local minimizer closest to the initial point. That's not what happens. So this misconception, this is also a misconception, this statement here. But if we don't converge to a local minimizer closest to the initial point, does that really matter? As long as we converge to a local minimizer, we should be happy, right? Do we always converge to local minimizers? Actually, we don't. So, this example is classic. You want to minimize x cubed. You start here at 1, x equals 1, and IP-opt converges in 13 iterations to a saddle point. So it is not true that nonlinear programming solvers always converge to local minimizers. That's also a misconception. But now I know that many people here are thinking, so what? We know that nonlinear programming solvers, they compute KKT points. That's the conventional wisdom. And a saddle point is also a KKT point. So is it true that nonlinear programming solvers always compute KKT points? Actually, that's also a misconception. To show why this is a misconception, we consider here a problem where we minimize some function f, which is shown here in the black line. And we have also added the constraint that this function should be less than 0. So the feasible set is here to the left in green. But now we initialize the algorithm here. So what will happen? Well, the solver will try to decrease the objective value and the infeasibility. And since they are the same, it's good to move to the right to this point here. That's a good point, or it's a better point for both the objective and the constraint value. So that's exactly what happens. So IP-opt converges to an infeasible point, even though the problem is completely feasible. And I think this is the most, fundamental misconception. People say that, I'm using a nonlinear programming solver. Of course, I will compute a KKT point, but that's not actually guaranteed. And I should point out that a similar example was presented at a presentation by Andreas Wachter, who is the developer of IP-opt, and Simon Bowley, who are both developers at Groby. They had a similar example like this a couple of weeks ago, and their talk is on YouTube. It was a great talk, so I recommend everyone to watch it. And then it's super weird, because if we start here instead, you think the same thing will happen, but it actually turns out that we first jump here with IP-opt, we jump back, we then jump to this point here for 3 iterations. And while it looks like we are stuck in the primal space, we actually make progress in the dual space. And somehow the solver just knows that in the next iteration that it jumps to this part of the space. So, I don't understand exactly why this happens. Very weird things can happen with these nonlinear programming solvers. But to summarize these misconceptions, these nonlinear programming solvers, they are not guaranteed to compute global minimizers. They are not even guaranteed to compute feasible points, even if one exists. And I would say that, this, when you read this, you become a bit depressed. Like it looks like a very, very sad story if we can't even compute a feasible point. But as it turns out, in practice, in my experience, these nonlinear programming solvers, they often work quite well. You might need to give it a good initial point, or at least not a bad initial point. But if you do that, these nonlinear programming solvers, in particular IP-opt, works quite well. So this is like the sad theory. We can't really guarantee anything in theory, but in practice, the story is not as sad. And finally, we have one last preliminary topic, namely constraint qualifications. So these nonlinear programming solvers, what are they trying to do? Well, their ultimate goal, the thing they are trying to promise the user is to compute a KKT point. And if you look at the derivation of the KKT conditions, one of the derivations is based on doing a linear approximation of the feasible set. So if you want these KKT conditions to be necessary for local optimality, you need some kind of assumption telling you that, okay, the linear approximation I make should, capture the shape of the feasible set. And there are conditions called constraint qualifications, which guarantee that this linear approximation captures the essential geometry of the feasible set And that implies then that a KKT is necessary for local optimality. So we are not going to talk that much about constraint qualifications in this talk, but a common one is LICQ. And if you have heard of it, that's great. If you haven't heard of it, that's also fine. But what I do want to emphasize is that when I started working on this nonlinear programming project, I wasn't really sure about constraint qualifications. I didn't really know if they actually matter in practice. I was kind of under the impression that constraint qualifications is a topic invented by mathematicians to write papers. But now I have actually converged to a different opinion, namely that LICQ actually matters in practice. That's what I think today. If you ask me tomorrow, I might say something else, probably not. But if someone in the audience has a different opinion, I'm super happy to hear about that after the talk. But my opinion right now is that LICQ actually matters for IBOPT, for practically solving nonlinear programs. So that was some theory about nonlinear programming. What can you actually do if you want to solve a nonlinear program? And I should make a disclaimer here maybe. When I say nonlinear programming, I'm thinking about classical nonlinear programming in the context of operations research. If you came to this talk and you thought that I would talk about stochastic gradients and machine learning, unfortunately, this is not that talk. So I'm just throwing out that disclaimer. When I say nonlinear programming, I'm talking about classical nonlinear programming. So suppose you want to apply classical nonlinear programming. How can you do that? Well, there are several excellent pieces of software that support nonlinear programming. So a couple of open source ones are YALMIP, JUMP, Pyomo, and Casadi. And commercial software packages also support nonlinear programming. So what do these modeling languages actually help us with? Well, in convex optimization, we remember that the main task, or one main task of the modeling language in convex optimization, is to take the high-level problem description and canonicalize it to this standard conic form. That's the main task in convex optimization. In nonlinear programming, the main task of modeling languages is different. So in nonlinear programming, the modeling language should provide the underlying solver with gradients and Hessians. And since the solver needs gradients and Hessians in each iteration, this means that there is much more communication between the modeling language and the solver. So if the modeling language is slow to compute these derivatives, then it will actually be the bottleneck instead of the solver. And this is a challenge. This communication here is, I would say, is a challenge compared to that. It's a challenge that doesn't arise in convex optimization, really. But here in nonlinear programming, the modeling language plays a more important role in this sense. So when you see these modeling languages, it is reasonable to ask, why do we need a new one? These software packages are awesome. Do we really need one more? And I asked myself that question when I started working on this nonlinear programming project. And so instead of just trying to reinvent the wheel, I tested these packages and I realized that they are very, very good if you know what you are doing, if you are an expert in optimization. But if you don't know what you are doing, Or if you are an expert who is very lazy, unfortunately, the expertise and the laziness, that's like a straight line with positive slope. So unfortunately, experts in optimization tend to be pretty lazy. So even experts can run into issues when they use these modeling languages, because you are sloppy when you formulate your problem. So you send a bad problem formulation to these modeling languages, and the modeling language will not try to save you. That is what might happen. So to show one example of when this happens, we can consider just a standard lasso problem. So this lasso problem is convex. So, if we wanted to solve it using a general purpose solver, we should of course use a convex optimization solver. But suppose we, for some reason, want to use a general purpose nonlinear programming solver. So the second term here encourages sparsity. So we expect that the solution will occur at a point of non-differentiability. And what existing modeling languages do is that they don't really care about this point of non-differentiability. They say that, oh, this objective function, it's differentiable almost everywhere. So let's just pretend that it is differentiable everywhere. And we provide derivatives, gradients, and Hessians to the solver, even though we might be at a non-differentiable point. Does that matter? I think it's, quite reasonable that we have an objective function that is differentiable in almost the whole space. But unfortunately, the points of non-differentiability are actually the points we care about. So it turns out that if you ignore this non-differentiability and you just provide derivatives using automatic differentiation, and you ignore this point of non-differentiability, then that might cause solvers to struggle. So to show a simple example of this, we use IP-opt, and we interface it using Casade, which is this famous nonlinear programming modeling language. And this is for a very small problem instance. And, I want to emphasize that this is a convex optimization problem. We expect that we should be able to solve it very gracefully. So if we look at the output from IP-opt, we see that, okay, it converges in 13 iterations. That sounds very reasonable. That's what we could expect using an interior point solver. So that's great. But then you see that it converged to a point with objective value 100 billion. Yeah, 100 billion. And that objective value is probably not the solution. But then you look even closer and you see that, okay, IP-opt actually crashes. It raises an error. So when you see this log, who should you blame? I think most people would blame IP-opt because the output you see is from IP-opt. IP-opt is the one telling you that, hey, I failed, sorry. So I think most people would blame IP-opt. But actually, I think we should blame the modeling language because it provided IP-opt with an impossible task. So, of course, we shouldn't blame anyone, but I mean, like, at least you should not blame IP-opt because I don't think this is IP-opt's fault.
Daniel, quick question. If I just go back and reformulate the problem using epigraph, right?
Yeah, that's exactly what you should do.
So then I would expect that IP-opt will work.
Yeah, that's what it does.
Yeah, okay.
Precisely.
Okay.
But now you have spoiled the rest of the talk. because that's what I'm going to talk about now.
I see that.
We all know what we should do. We should express this using an epigraph formulation and convert
Right.
it to a set of linear inequalities.
Right. Right.
But these existing modeling languages, they don't support that analysis. But that's what we do. So
Okay.
yeah, because this gives us the first glimpse of disciplined nonlinear programming. You are allowed to have non-smooth functions as long as we can reformulate it in a smooth way. That's essentially what disciplined means. Great question. So disciplined nonlinear programming is a new mathematical framework for how you're allowed to specify nonlinear programs. And in this framework, we distinguish between smooth functions and non-smooth functions. And if smooth functions, they can appear in any way you like. But we have rules governing how non-smooth functions can appear. And in the context of this talk, when I say smooth, I actually mean a function that is twice continuously differentiable in the interior of its domain. So I'm going to present to you, what rules you must follow. But I think it's very important to, before we do that, ask, what do you actually gain from following our rules? Do we guarantee you that we will be able to solve your problem to global optimality? No, of course not. Do we guarantee you that we will compute a local minimizer to your problem? No, of course not. We don't really guarantee you anything, honestly. Or we do guarantee you one thing. If you follow our rules that I'm going to describe, we guarantee you that we can take your problem and transform it to a problem that only involves smooth functions, so you will have no issues with non-differentiability. And also, in these transformations that we make to convert your non-smooth problem into an equivalent smooth formulation, in those transformations, we guarantee you that we do not introduce violations against constraint qualifications. So in other words, the transformations we do, we have a guarantee that they are not bad in some sense, because they give you smooth functions and you do not introduce LICQ violations. This is what we guarantee you if you follow our rules. And does this help in practice? Yes, it really does. I have seen many examples where the solver fails if we don't do transformations according to our modeling language. So this benefit actually, these guarantees, this benefit actually helps in practice as well. So that's what you get from following our rules. So what are the rules that we define? So in disciplined nonlinear programming, you construct functions that you want to minimize or maximize as usual in CivicPy. So you use atoms. And these atoms, we distinguish between three different categories. We have smooth functions, which are, twice continuously differentiable functions, essentially. And we also have non-smooth convex and non-smooth concave atoms. And then we define some very simple rules on how you are allowed to compose these atoms. And you can define these rules in there are like two approaches to state these rules. If you know about convex optimization, and in particular disciplined convex programming that I talked about in the beginning of the talk, if you know what disciplined convex programming is, it's extremely simple to to define the DNLP rules. You can actually define it in one line. So we say that a problem follows the rules in disciplined nonlinear programming. If it would follow the discipline convex programming rules whenever you treat smooth atoms as affine. So roughly speaking, if you look at your problem and all differentiable functions, just pretend that they are affine. If you pretend that, do you end up with a convex problem? If that's the case, then your problem is DNLP. I don't know if that sounds complicated, but it actually is not. So I guess my main point is if you know convex optimization to some extent, then you can learn these DNLP rules in 10 or 20 minutes. So it's really not it's not that deep. So yeah, it's great for students. Even students can understand it. You don't have to be a professor. Yeah. So for example, now we have implemented this disciplined nonlinear programming framework in CivXPy. So for example, now in CivXPy, there are some new atoms which haven't been available before because CivXPy was originally designed for convex optimization. So it required that every atom was either convex or concave. But now we have extended CivXPy with all these atoms that are neither convex nor concave. So for example, you can multiply two variables, you can optimize problems involving trigonometric functions, and you can even optimize functions involving the CDF of the Gaussian distribution. So all these atoms, they are new because they are neither convex nor concave, so they haven't existed, but they are, twice continuously differentiable. So, now we can support them. And I'm not going to talk that much about what we actually do under the hood to deal with the non-smooth atoms that exist in your problem. But at a high level, we follow this approach. So it turns out that whenever you specify a problem and you follow our DNLP rules, it turns out that if your original problem had a non-smooth convex atom anywhere, it can appear in a constraint or an objective. If there appears a non-smooth convex atom and you follow our rules, then we can guarantee that we can reformulate your problem in a way such that this non-smooth atom appears in an epigraph constraint. And the same thing if your original problem had a non-smooth concave atom. Then if you follow our rules, we can guarantee that we can find an equivalent formulation of your problem in which this non-smooth concave atom appears in a hypergraph constraint. We can guarantee this because you follow our rules. So now, essentially, you have taken all non-smooth parts of your problem and you have put them into epigraph and hypergraph constraints. And it is well known how to reformulate epigraphs and hypergraphs of non-smooth convex or concave functions into smooth formulations. So for example, the epigraph of the absolute value of x, well, we can just reformulate that as two linear inequalities. And before I gave this talk, I actually showed this slide to my mother, and she doesn't know that much math. She has some high school math background, but she looked at this slide and she looked at this constraint and she asked me, Daniel, how long have you studied now? Is it 8 years? And I was like, yeah, it's about 8 years. And she asked me, is this what you're doing for your research? Are you formulating the epigraph of the absolute value as two linear inequalities? I was shocked when she said that because I was finally opening up my heart to her and showing her my research, and she like made fun of me. So yes, of course, these transformations, sometimes they are super simple. You can do them yourself, right? But it is very error prone to do it sometimes. And also, there are some other non-smooth atoms which are much more complicated, which I guarantee you that it's much more difficult to formulate the epigraph of, for example, the Huber atom. So it is nice to automate these things, even though you could do some of them yourself pretty easily. So this Huber atom is quite interesting because, here we have the Huber function, which is quadratic, close to zero, and then it becomes linear. It looks very smooth, right? But actually in this, if you zoom in on this, at this point where it goes from quadratic to linear, it is differentiable, but it is not twice differentiable there. So this is actually a non-smooth atom according to our categorization. I told my mother this, but yeah, then it became too complicated, so she wasn't really impressed, I guess. But this is what we do under the hood. We transform epigraph and hypergraph constraints of non-smooth functions into smooth formulations in some sense. So finally, I want to show you a couple of examples. So we have implemented disciplined nonlinear programming in CivicPy in version 1.9. We support several different solvers, like IPOpt is the best open source solver out there probably. So I would recommend trying out that. If you're going to start with one solver, it's probably IPOpt. And so someone has to compute derivatives, right? And because the solver needs them. So we compute sparse Jacobians and Hessians via a C implementation. So we used to be the bottleneck when we computed these derivatives in Python, but then we re-implemented the derivatives in C, and now we're no longer the bottleneck. So just to show one example of what you can do, here we have a toy so-called circle packing problem. You have n circles, and the goal is to pack them into a very, very small square. And their radiuses are given. So you can optimize the circle centers where you can place the circles. And we have a constraint here saying that the two circles should not overlap. So that's a very non-convex constraint because you want to be outside a circle essentially. And if you stare at this problem, does it follow our DNLP rules? It actually does, because if you look at this problem and you just pretend, so where's the non-convexity? The non-convexity is in the inequality constraint. But if you just pretend that this smooth function here is affine, then you get a convex problem. So this is actually a DNLP problem.
Mm-hmm.
So now you can specify this in CivicPy using a regular syntax, and you can call a solver, and you get this result. And here we see that 72% So this packing is like pretty good because ideally you want the circles to cover 100% of the square, but here only 72% is covered. But we know that non-convex optimization problems, it can actually matter where you initialize the algorithm, right? So we support a flag which is called best of. So now if you specify best of equals 500, then we will solve your problem from 500 different initial points and return the best one. So if you do that, you actually find a solution that is 5% better in terms of coverage. And here we have the histogram of the solutions we find. So we see that sometimes we find a very, very poor solution, and sometimes we find a very good, and often we find a solution here in the middle. So this is the nature of non-convex optimization. The initial point often matters. So that's one example. I'm just gonna check where are we on time. Okay, so we are running out of time, but we have several more examples in the paper. So here we have an example on sparse signal recovery. Here on the left side, we have we have a sparse signal that we want to recover. And the classic approach is to minimize the L1 norm of the signal. That's a classic approach, and it is a convex optimization approach. What you can also do is to minimize, if you think about the L1 norm, it looks like this. But you can also minimize this a square root. And that square root is, can you wait? Oh, yeah. So you can also minimize the square root, and that it is sharper. So you get even sparser solutions. So here on the left side, we have the phase diagram for the non-convex approach. Here on the right side, we have the phase diagram for the L1 convex approach. And we see that we have better recovery for the non-convex approach in this case. But I guess the point is that, it's 4 lines of code. I guess that's the main point. It's very easy to specify these nonlinear programming problems in CivXPy now. Yeah. So that's basically what I wanted to say. Disciplined Nonlinear Programming is a new mathematical framework for specifying nonlinear programs. If your original problem just contains smooth atoms, if everything is twice continuously differentiable, then there are no rules that you must follow. But if you have some non-smooth functions, then we do some tricks which mitigates solver failures. And we have extended CivXPy with disciplined nonlinear programming, and we think it's ideal for students to play around with, and also for prototyping research problems. So that's everything I was planning to say. Thank you very much for listening. I'm very happy to take questions.
Thank you, Daniel.
Thank
It was a great talk. I think this is going to be very, very useful for teaching and also for research. So everyone, if you have any question, please go ahead and ask questions. So I will be stopping the recording now, so you can ask anything. So.